Welcome students. This session is about uses of influence line diagram. Let me just give you a little brief about theory part associated with this topic. Influence lines are used to find values of the function at section. Once again I'll repeat. In influence line diagram, we are targeting the function at the section. Suppose we are targeting shear force, bending moment or reactions or any other thing. We are targeting that function at particular location, particular section. So our observer is stationary, the section is stationary, the loads are moving. I have already explained this many times in the previous sessions, you can refer. So influence lines are used to find values of the function at a section for which influence line is drawn for a given system of forces. So for influence lines, there are mainly two systems of forces. One is series of point loads, which I have shown here, and the other system of forces is distributed loads, uniformly distributed loads. So either our beam is loaded with series of point loads, like a multi-axle truck, you can imagine, or a UDL, a uniformly distributed load, or a combination of both, right? So in practical cases, we need to study what happens to our beams mainly, or trusses, when this type of series of point loads or UDLs are moving from left to right. Looking further, the value of the function at a section is calculated by multiplying respective load value with the corresponding value of ILD. So suppose if, now let us see here, let me just write uses. So what I was trying to say is that if this is your beam and this is your, suppose this is X section, this is your ILD at X, then if your point load is this W1, this is ILD for S, ILD for SFX. So shear force at X will be nothing but intensity of load multiplied by this ordinate. Let this ordinate be A1. So shear force will be nothing but W1 into, similarly for bending, suppose we are having this W1, this is B1, so bending moment at X is nothing but into B1. So this is true when load is here. So it means that when load was moving from left to right, at some this t time you photographed the load, and at that time you wanted to see what is the shear force at X, what is the BM at X. You can easily calculate this. If after some time you can this load has moved from here to here, suppose this load moves from this position to next position, then the SFX will be this W1 into A2, this W1 into B2 for BM for SF similarly, right? So I hope this is clear. Now next, moving further, we will see first about the ILD for series of concentrated forces or series of concentrated point loads. So this is my simply supported beam, right? Now I have this series of point loads. I hope you are able to see. So earlier all the point loads are outside the beam, and slowly they will start moving, and they'll move from left to right and they'll pass through the beam. So during this motion, at some position, at some time, at this position of these loads, I want to calculate, this is my x, I want to calculate value of SFX and BMX using ILD. So how it can be done? That is, what will we do now? As I said earlier, we will see value of W1, multiply with that value with the ordinate of SF, ILD for SF, W2, ordinate of ILD, W3 ILD, and we will sum it up algebraically. Algebraically means using the sign convention also, plus, minus, minus. So this is the simple procedure to calculate SF at section and BM at section for concentrated point loads. Suppose I want like this. I want to photograph my motion of the loads at this time instant, at this position of load, and I want to calculate SFX and BMX. Okay, so let me just draw this point loads now. So this is one load W1, this is another load W2, W3, W4. Now using the concept, we already know how ILD for SFX looks like. So this is your section, this is your section, this will be like this, and this will be something like this. We already know the shape of ILD for SFX, so this will be nothing but ILD for SFX. Let this coordinate will be A1, this ordinate be A2, this A3, and the last one A4. With reference to concepts, we already know this is L minus X upon L and this is X upon L. This is your X distance and your entire span is L. Basics of ILD. Now, if I want to find out shear force at X when load position is this, then SFX due to W1 will be nothing but W1 into A1. SFX due to W2 is nothing but W2 into A2. SFX due to W3 is nothing but W3 A3. SFX due to W4 is nothing but W4 into A3. Right? Simple. So summing up all this shear force at X due to this individual load and multiplying with their corresponding ordinates, we can easily calculate SF. Now we can see that in this diagram, we know this is minus, this is plus. So our A1 and A2 coordinate in this case will come as negative, and our A3 and A4 coordinates will come positive as seen from the figure. So total SF at X is nothing but minus W1 A1 minus W2 A2 plus W3 A3 plus W4 A4. Similarly, for ILD for BMX, we know this is our ILD for BM. So ordinate below the load W1B, let it be B1, this one is B2, B1, B2, B3, and last is B4. Similarly, as SF, BMX due to W1 will be nothing but W1 into B1, then W2, B2, W3, B3, W4, B4. Right? So similarly, bending moment at section X due to this series of point loads at this time frame when they are at this position will be nothing but W1 B1 plus W2 B2 plus W3 B3 plus W4 B4. Very simple. Simple to calculate, simple to understand. So this is value of shear force at section X and value of bending moment at section X. When our load position is given by this. This peak we already know, that is x by L upon L minus x. Right. Second case, that is our uniformly distributed load. So first is series of point load, concentrated loads, and second is when beam is loaded with uniformly distributed load, UDL. Again drawing this beam. Let the section be somewhere here and our UDL be this. Intensity of UDL is W kilonewton per meter. Right. The length of UDL is small l. Distance of section from left support as always is small x and total span is L. This is support A, this is support B. Now in this case we want to calculate what is SF at X and BM at X. Same as we have done for series of point loads, right? Now in point loads we have these individual ordinates. So what is the difference in UDL? That instead of UDL what we have, I'll just draw the ILD for SF first and then I'll explain. This will remain unchanged. ILD for SFX will be always looking like this at the section. This is minus, this is plus. So instead of in point loads we were having W into that ordinate, W2 into that ordinate. Instead of that ordinates we have these two ordinates only, which is A1 and A2. So SF at X due to UDL is nothing but intensity of the UDL into this shaded area covered by that UDL in this ILD diagram. Shaded area in ILD. So if we see in our case, what is that shaded area? So this length of UDL is L. So this is a trapezoid. So what is the area of trapezoid? That is nothing but, so shear force at X will be nothing but intensity of load into A1 plus A2 by 2 into L. So this is UDL and this is shaded area. So SFX is nothing but intensity of UDL multiplied by the area of ILD for that function covered under that UDL. Similarly, if we see for BMXX. This is our ILD for BM, and we have ordinates under UDL, say for example B1 and B2. So what will be the bending moment at section X when this UDL which was moving, but you have captured it at this time. So for this time instance you need to calculate value of SF. If UDL is moved to another position, this value will change, that we already know. But so this value is at this position of UDL at when SF at X and BM at X. So this is W into shaded area in ILD, that is nothing but W into B1 plus B2 by 2 into L. So this is area of trapezoid. This is area of trapezoid, which is nothing but average of these two values multiplied by the length. If you are good with your centroid and moment of inertia concepts, there are many topics in which you will repeatedly get this type of requirement of calculating area, calculating CGs, moment of inertia. So it will be helpful. So this is value of ILD for shear force at X when load is at this position, and bending moment at X. So this is how it is calculated. So these are the major use of influence line diagram. Pay attention. This is major use of influence line diagram when you are photographing your load at some position. Load is in continuous movement, but when you want to calculate value of your function SF or BM at given position of load. So when load was moving from here to here, constantly these values are changing. But if you want to calculate what will be the value of SF and BM when load position is this. So when load position is given, you can calculate SFX and BMX using this methodology. So for concentrated load, this, and for uniformly distributed load, UDL, this simple calculation. Next, we will see a problem related to this concept further in ILD for determinate beams. Now we will see a problem related to the uses we have explained for the simply supported beam using influence line diagram. Let us use a series of point loads. There are 4 loads. (10 kilonewton, 12 kilonewton, 15 kilonewton, and 8 kilonewton. Each of them are 1 meter apart. So total span of the beam is 5 meters. And we have to draw ILD for RA, RB, and SF at section X and BM at section X. The section is given at 2 meters from left. As we know, easily we can calculate ILD for RA and ILD for RB. I think now we don't need to do any calculations for ILD for drawing ILD for R and RB. Simply we can draw ILD for RA will be this coordinate being 1. Now whenever we draw we are solving a problem and we are drawing ILDs, what we need to do is to find out these ordinates corresponding to the load position, whether it is UDL or whether it is series of point loads. We need to calculate these ordinates. Now this is a very simple triangle. This height is 1, so this will be, this is at 1 meter, so 1 meter, 2 meter, 3 meter, 4 meter. So dividing equal distances, this will be like 0.8, this will become 0.6, this will become 0.4, this will become 0.2. This is ILD for RA. ILD for RA. This is A point, this is B point. Similarly, we can draw ILD for RB. The coordinates will be 0.2, 0.4, 0.6, 0.8. This is ILD for RB. Right? This is very simple and very clear. Now let us draw. Let us calculate first this ILD for values RA and RB. Right? So value of RA will be nothing but these individual load values multiplied with these ordinates. So RA will be 10 into 0.8 plus 12 into 0.6 plus 15 into 4 plus 8 into 0.2. This is, I have already calculated, 22.8 kilonewton. This is value of reaction at A when load position is this. Similarly, so RA is calculated. Similarly, RB is 10 into 0.2 plus 12 into 0.4 plus 15 into 0.6 plus 8 into 0.8 equals to 22.2 kilonewton. We can easily calculate RA and RB using ILD concepts when given load position is known. Moving further, we will draw ILD for SFX and BMX. Let me draw it in the another, because it will not be accommodated here. Okay, let me use this. So ILD for SFX will be this section is at 2 meter here somewhere. So to this point it will be like this, and from here it will be like this. This will be positive, this will be negative. Let me show the values. So under the point load 10 kilonewton, the coordinate will be, this is, we already know that this diagram is ILD for RB, this diagram is ILD for RA. So these coordinates we already know. So this will be point, it was 0.2, right? This ordinate is 0.2, this ordinate is 0.4. Similar, this ordinate was 0.6, then 0.4 and 0.2. Right? This is ILD for SFX. Let us calculate value of shear force or let us first draw these diagrams and then we can later calculate the things. Let us draw ILD for BMX. So at this point, so this distance is 2 meter, this distance is 3 meter. Let us say now first for all these things, ILD for SF, ILD for RA and RB, it was very easy to find out these ordinates value. But for ILD for BMX diagram, ILD for BMX, this ordinate we know that it is x by L over L minus x, right? So let us call it this first unknown coordinate is B1, second one is B2, third one BB, B3 and fourth will be 4, right? So B1, let us calculate first. B2 will be nothing but x by L upon L minus x, that is 2 upon 5 into 5 minus 2, that comes out to be 1.2 meter. So our B2 will be 1.2 meter. Now using the simple trigonometry, we can calculate B1 as B3 would be 1.2 into 2 divided by 3, 0.8. B4 would be 1.2 into 1 divided by 3.4, right? How this has come? If you see this in triangulation, these ordinates is very simple. I hope you understand this. You already know this, but let me just repeat it. So this distance is known, right? We want to calculate B1. So if height is 1.2 and distance at 2 meter, what will be height at 1 meter, which is B1? So 1.2 into 1 divided by 2, and similarly for all these ordinates, right? So now we have calculated the ordinates. Now we need to calculate SF at x and BM at x. Now I have deliberately taken this problem which has a point load or a concentrated load directly on the section. When the load is on the section, the shear force value is not one value, it will be two values, SF left side and SF right side, right? So we have to find out two SF values. So SF left and SF right, we have to calculate. When we are considering left shear, the load on the section is to be considered on the right side. So considering left shear, consider load just right to the section X. When considering right shear, consider load just to the left, just left to the X, right? Let me explain it. This is my ILD for SF diagram. Now these are my load and this is the load position given, right? These intensities are already given, 10, 12, etc. Now when my this load, my W2, I hope it is okay. when my W2 is at the section, you can see in shear force diagram you are having two values at this ordinate. So which one to be considered? So when you are calculating left side shears, which is negative shear, what values to be considered, which ordinates to be considered, and when you are calculating right side shear, which coordinates are to be considered. It means that calculating SF at X, because you can see from the diagram that shear force at X diagram, it has two values. For X, it has got two values. It means that at this point, when load position is such that one of the load is at the section, SFX will have two values. Clear? If this load position would have been like this, then there would be no problem, because this ordinate, this load into this ordinate, which is minus, this load, this ordinate minus, plus this into this into this. Directly you can calculate SF at X. It will have only one value, right? Algebraic sum. But when position is like this, then at W2, which coordinate should be taken? Either it should be taken 0.6 or it should be taken 0.4. So the answer is, you have to calculate two shears, left shears and right shears. So left shear is nothing but when the W2 is just next to the section, it will give you left shears. It means that all the shear forces which are left to SFX, right? And when you are calculating shear force at right, you have to take this W2 just left to the section, which means that calculating all the shears which are right to the section. So when this, it means that this load is on this side, right? I hope this explanation is understandable. Now we can calculate left shear and right shear. So SF X left side will be nothing but 10, which is the load. Okay, so 10 kilonewton into this ordinate, which is minus 2.2. Then when we are calculating SF left, our 12 kilonewton load which is on section is considered just right to the section, right? So plus 12 into this ordinate, because load is on the right side of the section, plus 15 into 0.4 plus 8 into 0.2, and the answer I have already calculated is 12.8 kilonewton. So SFX left. Similarly, SFX right, it will be, now we are considering that our W2 load 12 kilonewton is just left to the section, so that we can calculate all the shear forces right side of the section, right? So when the position is like this W1 into 0.2 minus W2 will be on this side, so it will have this ordinate, and then the rest as it is. So it will be having 10 into minus 0.2 plus 12 into minus 0.4 plus 15 into 0.4, because this 15 is here, 0.4 plus 8 into 0.2. Correct. So this was the critical thing. So when you are considering left side shears, consider your load which is on section on right side, so it will have this coordinate, right side coordinate of the ILD, and when you are considering right shears, consider that load on left side, so it will have this ordinate. I hope this is this, like this, right? So this value is nothing but 0.8 kilonewton. SFX. This may look little clumsy at first, but if you understand it and solve 2-3 problems similar, you can easily understand things. If not, you can again repeat this video. You can rewind and forward with slower speed or faster speed with your comfort, and you can go to all the steps, all the concepts I have explained to reach to this calculation. Okay, so our SF is done, SF left is done, SF right is done. Next is to calculate BM. Let us calculate here. What will be? Let us not waste pages. So BMX is to be calculated. What will be BMX? Value of BMX is very simple. When you know the load condition and the load position, it is nothing but value of load multiplied with the ordinate of that ILD. So 10 into B1. B1 we calculated as 0.6. B3 we calculated 0.8. B4 0.4. So BM at X is nothing but 10 into 0.6, 12 into 1.2, 15 into 0.8. See, this will be meters, in meters. These ordinates will be having no unit. These are 0.6 units, 0.4 units. It doesn't have any unit, meter, mm, nothing. Because it is, you can see the equation x by L, x by n to L minus x. So there is no unit of distance. But here, you see this equation, x by L, meter by meter into meter. It means that this ordinate will be having the unit meter. And when you multiply this ordinate with the loads, you will get kilonewton meter. Normal concepts of bending moment. So your bending moment is BM at XX. I hope I'm, yeah. BM at X is nothing but 10 into 0.6 plus 12 into 1.2 plus 15 into 0.8 plus 8 into 0.4. I hope it is available in this also. Yeah, you can see this. Right. I will share this note with you. That answer is, so this is 6 plus 14.4 plus 12 plus 3.2. BMX is nothing but 35.6 kilonewton meter. I think now, understanding this problem very closely, you can solve this type of problems. Why I am telling this type of problem? Because if you can see, you can observe in this type, the position of load is already given. The position of load is already given. It is not asked that at what load position you will have certain values or maximum values or minimum values. This problem is as almost similar to our normal SFBM problem, but the only thing is, using this diagram, concepts of ILD are being incorporated. So this problem is what? Here your section observer is also stationary and load is also stationary, and you are using your concept of ILD because you want to know your function values at some load position, at your some, as I said, the photographed position. Right, so in this problem we calculate ILD for RA, we calculated ILD for RB, the diagrams, the values, ILD for SFX, the values, why we had to calculate two values, that also I have explained thoroughly, and this is ILD for BMX, values, ordinates. I hope that you will be able to solve similar problems of ILD of this kind, concentrated load. Say for example, instead of these 4 concentrated loads, any 3 loads would be given. The same procedure, you can calculate the thing. Suppose instead of these point loads, a UDL would have been given. You can calculate, nothing. What you will have to do, if this was a UDL, let me UDL. So if this was the UDL, right? If this was a UDL, then what would be a value of RA? So you'll have to just find out this shaded area and multiply with W. So this W into this shaded area will give you RA. Similarly, this W into the shaded area will give you RB. Similarly for SF, it would somewhere come here. So now here you don't need to calculate for left or right, because there is no single point load which is on this side or that side. So this UDL, so this shaded area, which is, so W into this shaded area, which is minus, plus this W into this shaded area. So we will get one value of SFX. Similarly, this W into this shaded area, you can calculate easily, normal trigonometry, and you can find out values of SFX, BMX. Next, we will be going for a major topic in ILD, which I call the significance of influence line diagram. I would like to explain that topic in next session, but which is mainly related to the maximum values. In this problem, in this session, we saw that a load position was given, but in actual problem, suppose you are designing a girder and your trucks are moving, it is not required to calculate values when the truck is at some position, but you need to find out values that when truck is moving from left to right, what will be my maximum value at maximum section. And if you can calculate that maximum value, you can design as per the maximum values. You don't need to go for other values, because when load is moving, you will have constantly varying values of shear force and bending moment. But you have to target that maximum value for which you will design your girder. So in next session, we will be starting that topic, which is in many books called as rolling loads, and to calculate the effect of rolling loads, the functions, parameters using influence line diagram. Thank you.